Now, so far, we've basically had the standard story that everyone tells you about climate change. You get light from the sun that gets in, but the light that goes out is blocked by carbon dioxide, and that makes the Earth warmer. But things are a little bit more complicated than this. And that was actually worked out originally, again, over 100 years ago in the late Victorian period. The basic trouble is, sure, carbon dioxide, particularly this bending mode, blocks light at this particular wavelength getting out. The trouble is it's too good at blocking this light from getting out. You can take a cylinder and fill it with the amount of carbon dioxide in the atmosphere in pre-industrial times, and that's more than enough to completely block the infrared radiation going out. So it's kind of like a brick wall trouble. How much light gets through a brick wall? None. If you make the brick wall thicker, does it change anything? No, it doesn't. Putting a second layer of bricks does not change the amount of light getting through because no light gets through anyway. And it was kind of the same with CO2. At those particular wavelengths, just past 10 microns, even the CO2 from hundreds of years ago, before we started polluting, was quite enough to block any infrared light from getting out. So if it's already blocked, adding more CO2 makes no difference, does it? That's what physicists thought back in the 19th century, and that meant that for a long time everyone assumed that CO2 was not going to have a problem. Sure, it blocks infrared light, and it is infrared light that cools the Earth down, but it's already blocked. It's not going to change anything having more CO2, it's just like making a brick wall thicker. But eventually, starting in the 1930s, the scientist called Callendar, this started to change. The reason is, sure, radiation from the Earth's surface at that particular wavelength, which is to say these wavelengths here, cannot escape. Doesn't matter whether there's human pollution or not, even hundreds of years ago it cannot escape. But radiation from a few kilometers up can escape. It's not just the Earth's surface radiating infrared, the atmosphere radiates infrared. And so it turns out that at that particular wavelength, that infrared wavelength, it's not radiation from the surface escaping, it's radiation from a few kilometers up, between about 5 and 7 kilometers up as it happens, on average. It does escape. And what happens when you add CO2 to the atmosphere is it becomes harder for this radiation from, say, 5 kilometers up to escape. So the atmosphere is only going to escape from a higher level where there's less atmosphere in the way. So what happens is, as you increase CO2, instead of getting radiation from the surface, which never escapes, you change the radiation from 5 kilometers escaping up to, say, the radiation from 7 or 8 kilometers escaping. Radiation will always escape, because the atmosphere gets thinner as you go up. There's always going to be some altitude where there's little enough CO2 above the radiation can escape. So all that happens is, as you change the amount of carbon dioxide, is you are changing the altitude from which the radiation escapes. Now, why does that matter? It matters because the atmosphere gets colder as you go up. So blackbody radiation is strongest when something is warm. So if radiation from the surface could escape, you get quite a lot coming out. But as you go up, you're going to get less radiation because it's colder up at 5 kilometers. And if you add more CO2, so it only escapes from 7 or 8 kilometers, it's even colder up there, so even less will escape. So you are reducing the amount of radiation that comes out, not by blocking or unblocking radiation from the surface. Radiation will always escape, it'll just escape from different altitudes, and what you're doing is you're pushing the altitude up. And because the atmosphere gets colder, up to the tropopause at 15 kilometers or so, that means you're getting less radiation. If the atmosphere got hotter as it goes up, as it does at some levels, actually adding more CO2 would make more radiation get out and would cool the Earth down. But for our case, the radiation is coming from the bottom part of the atmosphere. It does get colder as it goes up, so that is the mechanism behind global warming. And you can see this in satellite data. Here's a spectrum of the Earth obtained from a spacecraft, looking at how much radiation comes out from the Earth. And you see the clear windows over here. And then down here, between 14 and 16 microns, is the carbon dioxide absorption band. And you can see there is still radiation coming out here. It's much lower than on either side of it. And the reason why it's lower but not zero is because it's escaping from further up. And in fact, this is used by weather forecasters to map temperatures at different levels of the Earth's atmosphere. You can tune your instrument to this wavelength, and then you're measuring not what the temperature is at the surface, but what the temperature is 7 or 8 kilometers up, which is very useful for weather forecasters. So, radiation from the surface does not escape, but it can escape from higher up in the atmosphere. Increasing CO2 levels increases its altitude, and as it's colder up there, that reduces the radiation going out. The other effect is what CO2 also changes the radiation escaping at the edges of the spectral band. Remember, here is how much radiation gets through. As we increase the amount of CO2, you see down here it's completely blocked. But as you increase the amount, it's blocked over a wider and wider range. So this might be pre-industrial CO2, and it's completely blocked in the middle here from the surface, but there are still wavelengths towards the edges where it can get out, and as you increase them, these edge wavelengths start blocking things. So these are the two effects for carbon dioxide. One is it changes the altitude that radiation escapes, and secondly, the edges of the band are affected depending on the amount of carbon dioxide. This also explains why methane is also a serious greenhouse effect gas. Methane absorbs here and here, and it absorbs far less than carbon dioxide. But curiously enough, that means that methane is a much more serious problem. Because carbon dioxide fully absorbs, changing the amount doesn't change how much radiation gets out very much. But because methane is only partly absorbing, changing the amount of methane has a direct one-to-one effect on how much radiation goes out at these two wavelengths. So methane is a very potent greenhouse effect gas because it doesn't block things so much.